Hello Linux fans. Today we're going to discuss file permissions and special file permissions within the Linux operating system. First, let's talk about what file access is and what file access rights are so that we could fully understand what file permissions are. Remember that in Linux you have three different types of users as far as files go. You have the owner of the file. That's usually the creator of the file or the person that the file was created for. You have a group that owner is a member of. That could be like, let's say the owner is in the sales department. The owner would be the particular salesman. The group would be the sales department. And then you have everybody else in the organization. Let's say personnel or whoever, human resources, people not associated with sales. So basically, that gives us the owner is usually a person. The group is usually who that person is with as far as a subunit within the enterprise. And then everybody else is just whoever else has access to that particular system. So you could see how we want to control who has permissions to use different files within Linux. And this is one of the things that in Linux is really, really powerful. Let's take a look at the types of permissions there are in the Linux operating system. There's basically three types of permissions: read, write, and execute. The read permission allows users to see the file. They know it's there. They can read the contents, but they can't do anything else with it. Nothing at all. The write permission allows them to make changes or write to the file and is usually, but not necessarily, coupled with read permission. Execute the file is an executable file, meaning that that particular user with the execute permission can actually run the file. So anybody can read it who's got the read permission. People with the write permission can write to it as well as read it. That's going to be a little more restrictive because you only want authorized people that could change the file to be able to write to it. Because if you can write to it, you can change it, you can delete it, you can make a working file not work. So you really have to be careful about that. Executing is going to be yet even more restrictive because those are people that can actually run the code that the file will tell them to execute. And it could either be compiled code or interpreted code, determining whether or not it's a shell script or an actual compiled program in an upper level language. And of course you have two types of files. You have directories, which contain regular files, and then you have all your other types of files that are usually within the directories. So let's take a look at the summaries of some of the permissions. This table here pretty much summarizes what I gave you. And when you do the ls/l lowercase l command in Linux, you will see what your permissions are. And I go into that in some of my other videos, where you see the X's under read, write, and execute. When you do your ls/l, you will get a listing of the file, either your whole directory if you do not specify a name of your present working directory, or the specific file or files that you request permissions on. Directory permissions: read, list the files in the directory. Write, you could add new files to the directory. You can delete files from the directory, or you could even change existing files within the directory. And execute means you can actually run compilable code. So let's take a look at a sample of what an ls/l command might look like here. And I know this slide can be a little bit blurry, but kind of bear with me. Okay, we see here the ls-l command right there. Okay, then you see over here this D means it's a directory. Okay, these files here are ordinary files by the lack of a D. You see you have an RWX, read, write, and execute. This is all for the owner, these three. Then you have this RWX, read, write, and execute for the group. And then you have this RWX, read, write, and execute for everybody else. This number here is the link count, which is sort of out of the scope of this video. It's covered in other parts of the course. This field right here is the owner. Okay, this field here, facility in this case, is the owner's group. So this would be like the salesmen in my previous example. This would be the sales department, the owner and the group the owner belongs to. This is the byte count of the file. This is the date accessed, month, day. This is the timestamp. And this is the file name right here. So this is how you actually read your ls/l command and read what these actual permissions that we're discussing now actually are. Permission values. A little background on this. Linux was written way back when most computers ran on 3 bytes. Not today, where we're running 32 and 64 bytes in your average processor. Linux was written for 3-byte computers. So the read, write, and execute permissions were written as octal notations to be written in 3 bytes. So if you were to look in the actual computer, the octal value of the permission, you would see 1 octal digit. Okay, if it's a 0, the octal value of 0 right here, that means that the read, write, and execute are all 0, which would mean nobody has any permission to do anything with the file. Not a very practical set of permissions, so that's usually not used. Okay, and remember, each of your owner, group, and everybody else has its own set of permissions. So, in other words, each of the 3 groups, the owner, the group, and everybody else, would have 1 octal value. And each octal value has the 3 permissions encoded in it of read, write, and execute. An octal value of 1 would just be execute commands. Okay? And you have to look at it starting from execute, write, and then read. And if you know how to convert octal to binary and add the binary digits, that's how you could figure this out. The octal value of 2 would be binary 1, 0, which would be write only. No read, no execute. The octal value of 3, if you remember your conversion, would be binary 1, 1, which would be basically write and execute. No read. The octal value of 4 right here would be read, okay, because that's in the 3rd position, so that would be a binary of 1, 0, 0, okay, so it would be read, no write, no execute, and so on down the line, 5, 6, and 7. 7, and you're going to notice in certain times when you use the change mode command, you're going to want to change things to 7. That gives read, write, and execute privileges to whichever group you're specifying. So let's go on to the next. Permissions for access to courses, labs, and temps. Those are the files we used in our example earlier. Okay? No permission. You can't really do that much. Okay, the file name courses. The user would have read, write, and search. Okay, these are the permissions. Other would have no permission. Okay, in labs, if you remember what the permissions were going back, they would have 11777, which would be read, write, and execute for all 3. Temp would be read, write, execute, read, and read. That's referring back to the previous slide. Okay, if you want to change the access rights to a file, as I mentioned earlier, you would use what's called the change mod or the chmod command. Remember, in Linux, all commands are lowercase. So the purpose is to either set or change permissions within files or possibly even directories. Okay, because remember, in Linux, everything, even directories, is a file. So you have your change mod, your format, like in any Linux, your options, and your octal mode, in your file list. You could have multiple files in your file list. You could also, if you want to do it a different way, rather than using the octal mode, you can use symbolic mode. R for read, W for write, and X for execute, with either the plus or minus to add or take away those writes. And the R recursively processes through subdirectories, which sometimes, if you have a whole big subdirectory tree and you want to change all the subdirectories within a subdirectory and all the subdirectories within all the subdirectories, the recursive will do that for you. Okay, if you look at your symbols, and we discussed this earlier, U is user. If you want to add your operator, this is for the symbolic mode, you add the privilege, R would be the read bit. To remove the privilege, you would use a minus. To set a privilege, you would put equal. And of course, you have your user, group, and other. A could be for everybody, and UGO would be the same as an A. It would be basically all. Okay, there's also these other bits here, which we'll discuss later in this slide presentation. These are considered special permissions: the locking privilege bit, the group ID bit, mode bit, and the sticky bit. We will get to those. So let's look at some examples of the change mode commands and their purposes. If you use change mode 700, remember that's giving a 111 to the user and zeros in all three to everybody else. So what that's going to basically do is it's going to give read, write, and execute privileges for the owner, but no privileges to anybody else, because you're laid out in columns. And 7 is a 111 in octal for the owner, and in the group and everybody else, an octal 0 is a binary 0. Same thing. If you change mode to 740, okay, this 7 is going to give the owner read, write, and execute privileges. This 4 is going to give the group write and execute privileges, and it's going to give everybody else nothing. Right here, that's 0. So that sets the privileges for the courses to read, write, and execute for the owner, read only for the group, and no privileges for anybody else. If you want to change mode to 751, you do the same thing as far as your conversion go. You set the privileges, okay, to read, write, and execute for the owner, read and execute for the group, and execute only for others. Change mode 000 tilde, that's a special character, we'll cover that. That sets privileges for the home directory. Remember, the tilde in Linux always means the home directory. Okay, so we'll look at some examples of the change mode command and their purposes right here. Okay, this is your command, change mode. Okay, U is going to be the user equals RWX for the file courses. So you're setting the owner's access privileges to read, write, and execute for courses, but keep the group's others privileges to their present value, because you're not specifying any change. And in Linux, unless you specify a change, things stay exactly the way they are. Here, you're changing the mode for all to plus X. So what you're doing is A is everybody, plus is add privilege, X is execute in the file sample. So you're letting everybody on the system execute the file sample. Here you're saying G, which is the group, equals U. Okay, that basically, again for the file sample, you're making group privileges, right here the G is group, to match its user, G equals U, group equals user, or the owner privileges, again for the file sample. So whatever the owner, whatever privileges the owner has, the group will have. And here, change mode for G and O is going to equal, for the file sample, that's a blank. Blank is interpreted as a 0, so basically you're removing all the privileges. Okay, let's take a look at the actual bit layout within the record, within Linux itself. Okay, you see here, you start with bit 0 over here, and that's the execute bit, okay? For others access, remember it's owner, group, other, in that order. So you have execute, write, read, execute, write, read for the group, execute, write, read for the owner. Then you have this sticky bit, this GUID, and this SUID. These are your special privileges, which I'll be discussing in a minute. And then these bits are for specific file types, such as directories or other specialty types of files, which we'll get to momentarily. And as I said, this layout is seen when you use your ls-l command. And remember that L should be a lowercase l, not an uppercase L. That would give you a long list. The lowercase l is what you want to use here. So the position of access privilege bits for Linux files, as specified in the chmod command, again starting from right to left here, is again the other, execute, write, read, execute, write, read for the group, execute, write, read for the owner. Then you have the sticky bit, the GUID, the SGID, excuse me, and the SUID for what they call these special privileges. Okay, the default access rights. Okay, Unmask is a bitmap which is going to tell which permissions to deny by default on new files. This is for new files that are created within Linux. So let's say 22.0.22. If you look at what that's going to mean, it's going to be 0.0.0, read, write, and execute. This is for the owner. Okay, this is for the group. Okay, and this is for everybody else. But remember, Unmask, you want to think of it as kind of like the mirror image of permissions, because what you're doing with Unmask is the opposite. You're denying privileges. So what this example does is it's going to deny right for the group and the owner. Why you would want to deny it for the owner, I don't know, but that's the example in the slide. So this 0.2.2 would actually deny where that 1 is, which is right, because it's read, write, execute, read, write, execute for the group and for the owner right here. Okay, this should be everybody else here. This slide is wrong. I apologize for that. This 0.2.2 would actually deny write privileges for the group and everybody else, as is seen right here. Okay, Unmask with no parameters is going to return the current mask value. Unmask new mask, you can set a new mask value. And the unmask command usually is used in a startup file, such as your configuration files that runs when you start your shell. The SUID, okay, that is a special permission bit that allows executable files to run using the privileges of the owner of the files rather than that of the user of the file. And you would want to use that if you wanted to set up a file so that non-users could use the file as if they were the owner. And that would be very much like taking, let's say, members of the group and assigning them the same privileges as you would the owner of the file. And the change mode command for that would be U+S file list. Or you could use the change mode for XXX and the file list. That would show up in the ls-l command. In place of the user bit is an S if the file is executable. And you see that right here in the owner, read, write. And instead of execute, you have this S, which matches this S up here. Okay, and that means that this execute privileges here is basically coming because this SUID bit is set for this particular file. This is a very dangerous file to use, and I would not recommend any of my class do it or anybody else out there in YouTube land do it unless you're a very experienced system administrator, because you could create a lot of problems if you use it the wrong way, because you're basically giving the equivalent of root access to files for people that might not be your intention. So just think about it real carefully before you do it. The next thing I want to cover is the SGID, which is a special permission bit that allows executable files to run with the privileges of the owner's group. Okay, this G right here, okay, is for the group rather than the user. The other one on the previous slide was the U here for the user. This is the group rather than the user. So G goes with the G. And this, you set the command using the change mod. Okay, G plus S file list. You see this G here instead of a U. That sets the SGID bit so that the privileges of the owner's group is transmitted rather than the user of the file. And to do that, using the change mod with the symbolic is going to be the 2 with the XXX rather than the 4 that we saw on the previous slide. Okay, the sticky bit is a little bit different. Okay, the sticky bit actually has differences whether or not you're talking about Linux, but it has its roots in the early versions of Unix. And it is a special bit that can be used as follows. For a file, okay, this is for a file, it directs the operating system to keep the program in memory, if possible, after it finishes execution. That was especially used in early versions of Unix, because you have to remember, back in the early versions of Unix, we didn't have the beefy hardware we had today. So when code would finish executing, in order for code to execute, it's got to be moved to memory. So code back then used to be transferred from the storage device, today the equivalent of the hard disk or the solid state drive or whatever your mass storage is, into RAM. The processor would execute it out of RAM, then it would be put back onto the mass storage to be called up later if needed, but the RAM had to be cleared for the following commands to be executed because RAM was at a premium. Remember when the first DOS machines came out, they only ran on 640 kilobytes of RAM, and your hard disks were like 20 megabytes back in the early 80s. So you have to keep in mind, timeline here in evolution of computers. That was for a file. For a directory, it sets up to specify for a file here, if you wanted to keep a particular piece of code in memory, because let's say you had a program that you wanted to run the same piece of code over and over and over again, like a type of a loop, you wouldn't want it to execute, get sent back to the hard drive or tape drive in the dinosaur days or whatever, and then have to go back to RAM, back to the mass storage, back to RAM. So by using this sticky bit, it tells the computer, the processor, keep it in RAM, system memory, after it's done executing, so it can keep going back to RAM and executing it. That would make the program run much, much faster and save on input-output I/O speed between your RAM and your mass storage device, be it a hard drive or a tape drive or solid state drive. For a directory, it sets up in such a way that not only the owner of the directory can delete or rename the files from the directory, even other users have write privileges, okay? And that's temporary, okay? You want to be careful with this one because, again, whenever you give anybody else besides the owner privileges, especially to rename or delete, okay, you want to be careful with that. But the sticky bit for a directory sets it up so that only the owner of the directory can delete or rename files from the directory, even if other users have write privileges. So this safeguards the owner, basically, because the way this is written, only the owner can delete or rename files, even if other users have write privileges. So, thank you for watching. I hope you all learned, and I hope that you enjoy learning Linux.